You know, when you think about the copper in our phones or in our power lines, you might picture these big, shiny chunks of metal coming out of the ground. But that's not how it works at all. It's actually trapped as tiny, microscopic particles scattered throughout literal mountains of rock. So the real magic of modern mining isn't just the digging. It's the incredibly clever chemistry they use to separate that valuable metal from all the worthless stuff. So let's dive in and see how they pull it off.
So, that really is the big question, isn't it? After you've crushed a mountain down into something that looks like fine sand, and only a tiny, tiny fraction of that is actual copper, how in the world do you pick out just the valuable bits? I mean, you can't exactly do it by hand with a pair of tweezers. The answer, it turns out, is a kind of chemical wizard.
And that wizardry is called froth flotation. The core idea is just brilliantly simple. If you can't pick the copper out of the rock, you make the copper float away from it. To do that, we're going to use a very specific chemical recipe to make those copper particles absolutely hate water and love air. That way, they can just hitch a ride on a bunch of air bubbles straight to the top, leaving all the junk behind. Now, to make this happen, you need a whole team of chemical agents, and each one has a very specific job to do. Think of it like you're assembling a crew for a heist. Every single member is absolutely critical for the plan to work. So let's meet the first and maybe the most important player on the team. First up, you need a talent scout. You need somebody who can go into a massive crowd, spot the one person you're looking for, and make them feel special. Well, in our chemical heist, that's the collector. Its one and only job is to find those copper particles and attach itself to them. And here's the key part. When the collector latches on, it's basically giving the copper particle a little water repellent jacket. All of a sudden, that particle becomes what we call hydrophobic. It hates water. And that, right there, is the essential first step to getting it to stick to an air bubble instead of sinking. Now, the thing is, not all collectors are created equal. You've got your main workhorses like xanthates, which are great all-rounders. But then you have specialists like DTCs. These guys are super strong, really fast-acting, and they're used as boosters to snatch that last little bit of copper. It's all about picking the right tool for the job based on the ore you're dealing with. And this gets right to the heart of the central challenge in flotation. See, if you use a collector that's too strong, yeah, you might get more copper, which is good, but you also start accidentally grabbing things you don't want, like pyrite, fool's gold. That just makes your final product less pure. So it's this constant balancing act between quantity and quality. Okay, so our copper has its water repellent jacket on, and it's ready to float. But it needs a ride to the surface. So let's bring in the next member of our crew, the frother. This is the one responsible for creating the perfect bubble elevator. The frother's entire job is to manage the bubbles. You need bubbles that are just the right size for the copper to latch onto, but they also have to be strong enough so they don't pop before they make it all the way to the top. A good frother creates this stable, consistent layer of froth that acts like a conveyor belt, carrying our precious copper safely to the surface.
So what are these frothers? Well, in the industry, the big one you'll hear about is a chemical called MIBC, along with some other alcohol and polyglycol blends. You can really think of them as the unsung heroes of the operation. They don't get the glory of actually grabbing the copper, but without them creating that stable bubble structure, the whole separation would just completely fail.
And just like with the collectors, getting the dose right is everything. Add too little frother and your bubbles are too weak. They'll burst and all that valuable copper just sinks right back down to the bottom. But if you add too much, the froth gets too stable and it starts carrying up all sorts of worthless gunk right along with it. It is a razor's edge. All right, so we've got our copper tagged and ready to float, and we've got our bubble elevator running. But what about everything else that's in that slurry? Remember that pyrite we mentioned? We need a bouncer to keep all the unwanted minerals out of our VIP section at the top. And that is the job of depressants and modifiers. Depressants do the exact opposite of collectors. They actually target the waste material, like iron sulfides, and make sure they stay hydrophilic. In other words, they make them love water. This ensures that those unwanted particles just ignore the air bubbles completely and sink to the bottom, right where they belong. And why is this so critical? Well, if that pyrite gets into your final copper concentrate, it doesn't just dilute the purity. Smelters will actually charge you hefty penalties for it. So using depressants isn't just a matter of good chemistry, it's absolutely essential to making an economically viable product. Now, we get to the master controller of the entire operation, the pH level. This whole chemical system is incredibly sensitive. By adding a modifier, and it's usually just simple lime, metallurgists can carefully control the chemistry. They create an alkaline environment, typically between a pH of 9 and 11, which is the absolute sweet spot to make everything else work correctly.
And this right here really drives the point home. A tiny little shift in the pH can cause your collector to completely stop working, or it could make your depressant fail. Getting the pH just right is what allows the collector to stick to the copper and the depressant to stick to the pyrite. It's the foundation that this entire chemical house is built on.
And finally, there's one last specialist we should mention, the activator. You see, sometimes a copper mineral might be a little tarnished or oxidized on its surface, and the collector just can't get a good grip. An activator comes in and basically cleans up the mineral's surface, preparing it so the collector can finally attach properly. So, we've met the whole crow. The collector, the frother, the depressant, the pH modifier, and the occasional activator. It's quite a team. Now let's see how they all work together in a real-world strategy. So here's a look at a pretty typical, though simplified, recipe. You've got your collectors to float the copper, your frother to make stable bubbles, and notice here how lime is actually pulling double duty. It's not just the pH modifier, it's also the main depressant for the pyrite. It's a really elegant and interconnected system when you see it all laid out.
And this chemical recipe isn't just dumped in all at once. It's applied in stages. First, in the rougher stage, the goal is maximum recovery. Just grab everything that even looks like copper. Then, that material goes to the cleaner stage, where the focus shifts to grade. You're trying to remove any impurities. And finally, the scavengers make one last pass to catch any copper you might have missed.
So look, if you take just one thing away from all of this, let it be this right here. The entire science of flotation is a constant, delicate trade-off between recovery, which is how much total copper you get, and grade, which is how pure that copper is. And the kicker is you can't maximize both at the same time. Which leaves us with a final, kind of mind-boggling thought. The exact chemical recipe we just talked about, it changes for every single mine in the world, because every single ore body is different. The real genius of a metallurgist isn't just knowing the chemistry. It's the constant testing and fine-tuning needed to find that one perfect recipe for the millions of tons of unique rock flowing through their plant day in and day out.